All right, property of logarithms here. We're going to deal with all the properties, or a bunch of properties that you commonly use with logarithms. So the first thing we're going to do in order to figure this out, you need on a calculator, whether it be a graphing calculator or a scientific calculator, go ahead and add log base 4 or log base 10 of 4 or log of 4 plus log of 5, and then multiply the log of 4 times 5, and then do the same thing for log of 1 plus log of 3 and multiply those two. Now if you do that, you'd find that when you add those two up, log 4 plus log 5, you get 1.3010 if you round to 4 decimal places. And when you multiply log 4 times 5, you end up with the exact same thing. Okay, and then if you go through and do log 1 plus log 3, you end up with 0.4771. And then if you do log of 1 times 3, you get 0.4771, the exact same thing. The patterns there, we can go ahead and complete this following by kind of observing these patterns. If we have log of m plus the log of n, notice the bases are the same. They're both base 10 here. Then that's equal to the log of m times n. That's what we're seeing here. Log of 4 plus the log of 5 is equal to the log of 4 times 5. Log of 1 plus log of 3 is equal to the log of 1 times 3. So a conjecture we could make, just kind of know what we know about math, if we take log of m and log of n and rewrite it to log of m divided by n, well, you can kind of piece these two together. Think if you're multiplying, you're actually adding the logs. So if we have division, we are actually subtracting those two. So that would be log m minus log n. Okay. Let's kind of demonstrate two properties that we deal with in Algebra 2 here with logs. All right, the next thing is we're going to demonstrate one more property. We're going to graph log of x cubed and 3 log x. All right, and then we'll do the same thing for log x to the 5th and 5 log x. Okay. And I went to Desmos here, but you could do it on a graphing calculator. Okay, so we're going to go ahead and put y equals log of x to the 3rd. Okay, and then let's go y equals 3 log x. And you'll notice our line, when we put that x in, it changes colors. It actually changes to that same color right there. Notice we'll actually make it even there we go. So, and we can do that here. Notice they're the exact same line. Okay. So you end up with that same line. Okay. And the same thing would happen if we change this to the other, which was log of x to the 5th and 5 log x. We end up with the same line there. Okay, so kind of thinking through that, if we use that to the graphs to complete this statement, log m of k is actually equal to, well, we'll bring that k out here, just like we did with this 5. We bring it out here, and you end up with 5 log x. That's equal to k log of m. K times the log of m. All right. So let's go ahead and put those properties down here completely on the next page here. And we demonstrated was, it's actually called the product property. And it's where you take the log, and we're going to actually put the base in here, base b of m times n is equal to log base b of m plus log base b of n. And like I said, that's actually called the product property. So we'll write that off to the side here. Okay. Log base b of m over n is actually equal to log base b of m minus log base b of n. Okay? And you might guess it, but that's actually called the quotient property. And then the power property. Power property says log base b of m to the k power of k is equal to, we bring that k out front, k times log base b of m. Okay, and then we have two other properties that we've already dealt with. We have log base b of b, that's equal to 1. And then we have log base b of 1, which is equal to 0. Okay, so we want to recall those. So how do we use these properties? Well, a couple different things. First, it's nice to have these properties so we can combine logs, we can expand them, we can condense them. We also, using those properties, can evaluate logs if we know what an approximation for a log is. So for instance, if we know log base 6 of 4 is approximately 0.774, and log base 6 of 5 is approximately 0.898, we could actually evaluate that by saying, you know, I have log base 6 of 4 over 5. So really, when I'm dividing the 4 over 5, I can expand it to look like, or expand it using the quotient property to log base 6 of 4 minus log base 6 of 5. One quick note, when you're making your bases, make sure they actually look like they're in the subscript. Okay, so log base 6 of 4 is this, 0.774. And we're subtracting log base 6 of 5, which is 0.898. Okay, actually putting those together and doing the math there, that is negative 0.124. So log base 6 of 4/5 is actually equal to negative 0.124. And we've used those two logs to calculate that. So when we're doing something like this, what we want to do is look at the number. So log base 6, these are both log base 6, but how can you make a 20 using 4 and 5? Well, I know I could think of that as log base 6 of 4 times 5. And I know that's actually equal to, the product property says if I'm multiplying, I'm actually adding those two numbers. Log base 6 of 4 plus log base 6 of 5. And log base 6 of 4 we know is 0.774. And log base 6 of 5 is 0.898. Combine those, we end up with 1.672. That is what log base 6 of 20 is. All right. This next one we could do it a couple different ways. You can think of log base 6 of 25. You can either think of that as 5 squared or 5 times 5, however you want to do it. If I think of it as log base 6 of 5 to the second power, then I can use the power property to bring that 2 out front to write that as 2 log base 6 of 5. And then that's just 2 times log base 6 of 5. So 2 times log base 6 of 5 is 0.898. And 2 times that is 1.796. Okay. The other thing you could have done there, if you wanted to, you could have thought of it as log base 6 of 5 times 5, which would have been log base 6 of 5 plus log base 6 of 5. And notice you have 2 of those, so that ends up becoming this right here, right? Because we have 2 of the same thing. All right. Here, last one here. Notice 64. To write it either 4 or 5, we have to think to ourselves, well, 4 goes into that, but it goes into it 16 times, so 16 times 4. Or you could think of it as 4. 64 can be written as 4 to the third power. So we could think of that as log base 6 of 4 cubed, which then becomes 3 log base 6 of 4 when we apply the power property, which means 3 times 0.774, that's what log base 6 of 4 is, which becomes 2.322. All right. So that's how can you do this. Usually, like back in the day, you had to have tables of logs that you would use. Someone's actually calculated them out. Many calculators, especially graphing calculators, deal in different bases now, so you can use that. Otherwise, you'd have to be given these values or calculate them out yourself in order to evaluate these logs. Okay, let's practice expanding logs, just kind of applying our properties. All right, so I look at this first one, log base 3 of 6x to the 7th. I look at it as having log base 3 of 6 times x to the 7th. Whenever I see multiply, when you're dealing with logs, you have to think addition. So that's log base 3 of 6 plus log base 3 of x to the 7th. Okay, so I've expanded that. I broke apart the multiplication through adding. Notice I keep the same log for both of them. They're both log base 3. 6 times x to the 7th. And then note that I have x to the 7th here. Well, that x to the 7th, this 7 can end up moving out in front by applying the power property. So when you're expanding, you should do that. So that log base 3 of 6 stays the same, but we bring the 7 out to the front, we get 7 log base 3 of x. You have now expanded that completely. Okay? Now please note the difference on the second problem. Okay, I put these two on here so that you can kind of see the difference. This one has the 7th just being raised, or the x just being raised to the 7th. This has the 7 on outside of parentheses. That means it's 6 to the 7th and x to the 7th. So rather than breaking it apart using addition and then applying the power property, in this situation, you would apply the power property first. So you'd have 7 log base 3 of 6x. So bring that power out and then break apart using your addition. That becomes 7 log base 3 of 6 plus 7 log base 3 of x. Okay, so note those two. All right, let's try another one here. You'll notice the rest of them also look familiar, or I'm sorry, similar. Okay, so whenever you see that division symbol, you have to think subtraction. And on the top, you have multiplication, so you have to think addition. So dealing with just the top part first, that would be the natural log of 3 plus the natural log of x to the 9th. And then on that bottom part, you'd have minus the natural log of 5. Okay? And then we'd want to apply the power property. So we'll bring this 9 out in front. So we get the natural log of 3 plus 9, the natural log of x, minus ln 5, natural log of 5. Okay, notice the similarities between that problem and this next one. We still have 3x to the 9th on top. So that's not going to change. That 3x to the 9th is represented by this. So we're still going to have the natural log of 3 plus 9, it's not plus 9, okay, excuse me, yes, plus 9 natural log of x. But then on the bottom, we now have an extra y there, so we are subtracting the natural log of 5 plus the natural log of y. Notice you're multiplying here, so we're adding those two, but we're subtracting that whole quantity. Now what happens, you have a negative outside of parentheses, you have to distribute that. So that becomes minus natural log of 5 minus natural log of y. The more you do this, you'll just put minus minus, okay? And then this part here stays natural log of 3 plus 9 natural log of x. So whatever you have on the bottom, they both will be subtracted. Okay? Notice this next one, we just keep adding to the bottom. The top has stayed the same, so we still have natural log of 3 plus 9 natural log of x. And on the bottom now, we're going to be subtracting that. So we're going to be subtracting natural log of 5 and the natural log of y squared. Okay, the one extra piece here is we're going to have to bring that 2 out in front. So the end result, natural log of 3 plus 9 natural log of x minus natural log of 5 minus, or 2, natural log of y. Okay, so after expanding, let's actually work on condensing. So putting them back together. All right, so condense each logarithm. So you have log base 10 of 2 and log base 10 of x, or log 2 log x. Remember, if there's no base, it's always base 10. Since you have the same thing, same base, we're going to keep that base. When we subtract, we actually divide first by second. So 2 over x. Okay, looking at this next one, I look at this and I see log of 7. I see 2 log of 7. You can't have that 2 out there, and I see log of 7. So first thing I need to do is I need to get rid of this 2 so I can deal with it. And we can bring that in. So I now have log base 7 of 3 plus log base 7 of 4 squared minus log base 7 of 9. Okay, well, that's log base 7 of 3 times 4 squared. And that minus means I'm dividing it by 9. Now I can actually simplify this here, right? I know that 3 and 9 I can cancel. Make that a 1, make that a 3. All right, so it actually end up with log base 7 of 16 over 3. All right. Okay, let's go ahead and do this next one here. So natural log, 3 natural log, and natural log. So this 3 we have to deal with. Bring that in. So we get the natural log of 2 plus natural log of 3 cubed minus natural log of 6. Okay, so this addition, we're going to keep the natural log. Addition means multiplication there. So that's 2 times 3 cubed. And then subtracting. So we've got to divide by 6. Okay, I look at that and I know I can do a lot of different simplifying. So first thing, this is 27. Right, 3 times 3 times 3. So 2 times 27 is 54. Okay, so let's write that. Natural log of 54 over 6. Which actually, 54 divided by 6 is 9. It becomes natural log of 9. All right, let's note box that. One last thing, can you combine natural log of 3, or excuse me, the log base 3 of 6 plus log base 2 of 5? And the answer is no. Why? They have different bases. Okay, they have to have the same base. All right. Hopefully you're pausing and trying some of these. Okay. There's one last concept I want to deal with, and it's actually called the change of base formula. Okay. So there'll be times when it's helpful to change the base of a logarithm. For instance, if you'd like to evaluate a log on a calculator, that will only evaluate common logs or natural logs. So for instance, a scientific calculator. Okay. Most scientific calculators, or a lot of them, a lot of scientific calculators will only evaluate natural or common logs or natural logs. In my class, you won't be able to use anything but a scientific calculator on your exams there. Okay. 8 to the power of n equals 12, which there's not a power of 8 that goes to 12 or a whole number power. Okay, so it's hard to solve that intuitively. So if you can't solve it in exponential form, I've always told students, write it in log form. So you have log base 8 of 12. Still, it's hard to calculate. So let's try another way. Let's go back to our original equation. And just like trying to solve an equation, maybe like taking the square root of both sides, let's apply the log to both sides. So by taking this, and I'll write it out over here, but I have the steps there. If I have 8 to the power of n equals 12, and I say, okay, I'm going to go ahead and apply the log to both sides. I'm going to say I want it to take the log of that side and the log of this side. Okay? What that would end up doing for me is I would then have log base 10 of 8 to the power of n equals log of 12. And notice now you start kind of looking at it and you go, hey, I can take that and I move that out there using the product or the power property. So I have n times log of 8. My variable is out of the log. It's out of the exponential form. And now if I want to get n by itself, I just divide both sides by log 8. So I get n is equal to log 12 over log 8. And notice both of these are base 10. And you can use your scientific calculator now to solve that. It's actually equal to approximately 1.19. Okay, and that's what we've done here. I've kind of shown all those steps and tried to explain them. Well, what we've done is we've actually done the change of base formula here. Notice log base 8 of 12 right here is equal to log base 12 over, or excuse me, log of 12 over log of 8. How do we know that? Well, because this equals n and this equals n. So if they both equal n, then they equal each other. Okay, that's the change of base formula. The change of base formula says log base b of m is equal to log of m over log of b. Okay, or the way I like to remember it, if it's in the basement already, the base goes to the basement. Okay, the bigger number goes on top. Okay, a single log becomes 2 logs. So please don't confuse with this with the quotient formula. Okay, remember the quotient one says that you are dividing and you'll have a single log here. So don't confuse it with this formula right here. Or this property, excuse me, not formula. Okay? You don't want to confuse those two. Notice this division just has a single word log, whereas the change of base, you have log over log. Okay, and you can actually change it to any base you want. So really, you can make this whatever base you want. You could put c here because it could be any base. Usually we go to base 10 or base e, the natural log, but it could be any base. And I'll show you an example of when you do that. So let's write this as a common log and then evaluate it. All right, so in other words, remember the common log means base 10. Okay, so log base 9 of 12. Writing that as a log base 10, we would take this. Remember the base goes to the basement. So we'd have log of 9, and then 12 goes up. That's log of 12. And we actually divide those. We've got it written out here. It's 1.1309. Now I want to point out this next one says the same thing. Okay, but it says write it as a natural log and then evaluate. So exact same problem. If I want to write it as a natural log, I do it the same way. Just rather than base 10, I go base e. So I go natural log of 9 and natural log of 12. And if I divide those, they better be the exact same value. These two things better be the same. Why? Because the problems are the same. Right? And you're just changing the base to solve, not changing the answer. In fact, you can write it at any base you want. You could say log base 7 of 12 over log base 7 of 9 if you really like base 7. Just the problem is, I don't know what log base 7 of 12 is, and I don't have a calculator to help me with that. And I 7 of 9 is, and my calculator doesn't work in that. So I'm not going to use that one. That's why I use natural log or common log, because my calculators work in those. Okay, we'll go to common log again here. So this is going to be log of 7 over log of 4. We divide those, we get 1.4037. Now if I'm going too fast, then pause it here. Natural log, just now natural log of 6. And natural log of 10. Do the math, 4.12 and 6. All right. So when might you change a base to anything other than a common log or natural log? We'll actually see down on this problem down here. Okay. Before we do that, I want to just point out you can write it as anything you want. You can change it to any base you want. And notice you can go backwards here. If I want to write this as a single log, so notice my bases are the same. Okay, this is like after I've done the change of base formula. Okay, so if I look at it and go, my bases are the same, I could take that, right? And I could say, well, that just means this is in the basement, so that's going to be my base, and this is my big number. Okay, so notice if I said, hey, apply the change of base to formula to this, well, that would become log of 7 over log of 5. Okay, notice I don't have a 6 here. Okay, really, whenever you see logs in this format, you can change this base right here to anything you want. We could have said it's going to be now base E. Okay, we could say it's going to be base 10, which we've actually done right here. We just don't show the 10. We could say it's going to be base 8. It doesn't matter. It's up to you what you want your base to be. Okay? I just did the intermediate step where I rewrote it like this and then put it in base 10. And this approximation is 1.2091. Change of base formula is really, really helpful like that. So when might we use a base other than a common log or natural log? Well, when I look at this, log base 7 of 16 and log base 7 of 32. I look at that and I go, hold on. 16 and 32. Those are both base 2. So I could think of this as log base 7 of 2 to the 4th power. Right? 16 is 2 to the 4th. And I could think of 32 as 2 to the 5th. Log base 7 of 2 to the 5th. Now, if I'm dealing with base 2, or excuse me, if I'm going 2 to the 4th and 2 to the 5th, it makes sense to change base 7 to base 2. So let's do that. Let's just write it as log base 2 of 2 to the 4th. And log base 2 of 2 to the 5th. Some may go, is that legal? Mathematically, yeah, it is legal mathematically. They're already the same bases. You can make those bases whatever you want. Okay? And now looking at this, I can apply the product property. Bring that out in front. And bring that out in front. Or excuse me, not the product property, but the power property. So that becomes 4 log base 2 of 2. And this becomes 5 log base 2 of 2. And 4 log base 2 of 2. Well, log base 2 of 2 is just 1. That says 4 times 1 and 5 times 1, which is just 4/5. Okay? So you've evaluated it without using natural log or common log, and you could use those, but you'd still get 4/5 or 0.8. All right. I think that's it. Yep, good lucky.